All right, section 7.1 is law of sines. So it's going to be everything law of sines. You might remember this somewhat from Algebra 2 or pre-calculus if you put pre-cal. So this is a chart that basically lays out when you use law of sines versus when you use law of cosines, and it all has to do with what given parts of the triangle that you have. So first of all, law of sines and law of cosines is used to solve non-right triangles. So everything we've done so far, basically using trig functions, is based on the triangle being a right triangle. So with law of sines and cosines, it takes into consideration oblique triangles that are not right. So in the cases here, we have the different cases are angle, 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 side, angle, or angle, angle, side, side, angle, side, 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 or side, side, angle. So it sounds like a little bit like geometry when you're doing triangle congruency or triangle similarity. With this is, so this is going to be a situation. So this is different. We're not trying to prove it's not two triangles. We're looking at one triangle. And when you know all three angles of one triangle, that this says this case cannot be solved. So knowing all three angles, all three sides does not determine a unique triangle. I think it should say all three angles. It's a typo. Knowing all three angles does not. So there are many different triangles that can have the same size angles. That's why you can't use that method to prove congruency, because you can have two triangles have exactly the same angles, but are not anywhere near congruent. It does, however, give you similarity. So if they have the same size angles, they will be similar triangles, just not congruent. So that one's out. All right, the second one is if you know two angles and a side, and it doesn't matter if the side's between the two angles or not between the two angles. If you just, anytime you know two angles and a side, you will be able to solve that triangle. It means find all the other missing parts. You'll be able to find the third angle, of course, because it's just the 180-degree rule. If you know two angles, you know the third. But you'll be able to find the other two sides as well. But you would be using law of sines in that case. That's just the rule, the formula you'll use. All right, in the case of knowing two sides and the included angle, that means the angle between the two sides. That would be you would not be able to solve that with law of sines. You would have to solve that with law of cosines. As in, if you know all three sides, if you have side, 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 so you know all three sides of a triangle, you would be able to find the angles if you use law of cosines. And then finally, this is called the ambiguous case. Remember, when you in geometry, when you could not, this is not one of your 5 congruency methods. There is no side-side angle case. It did not guarantee you congruency between two triangles if you had two sides and a non-included angle of one triangle equal to two sides and the non-included angle of the second triangle. The angle had to be included, had to be the angle between the two sides. And there was a reason, because knowing two sides and an angle, there's two different triangles in some cases that can have those two sides and the angle and them not be the same triangle. So it did not guarantee congruency. And it kind of leads into this, which is if you have two sides and an angle, it's possible that there's no triangle that's possible. That contains those parts. It's possible that there could be two triangles that contain those parts. So finding the extra angle, you might have to, it could possibly be two totally different triangles that have those parts. So you might have to solve two totally different triangles, and that's why it's known as the ambiguous case, because it could be no triangles, it could be one triangle, and it could be two triangles. So the side-side angle is going to be the case that is a little special, that we'll look at in a whole different section all by itself. And if it is that case, then you can either use law of sines or law of cosines. So we'll see when we get to an example what we're talking about there. So we're going to really focus in this section on this angle side angle or angle angle side, because this is the law of sines case. And then we'll spend section 7.2 looking at these two, and then 7.3, I believe it is just the ambiguous case. And then we've got some just applications. All right, so what is law of sines? So law of sines is this is the formula for it. So remember, little a is the length of side A divided by the sine of angle A. So it's a ratio. So these are proportional. So every side divided by the sine of its opposite angle are equal. So remember, side A is across from angle A, side B is across from angle B, side C is across from angle C. So A over the sine of A equals B over the sine of B equals C over the sine of C. Nothing special about this as far as we could put sine A over angle, or sine A over side A equals sine of B over side B equals sine of C over side C. It would be the same thing. So you could turn these all upside down. It would be the same ratio, same proportion. So that's just one way of looking at it. All right, let's go through. So basically, you're going to have two sides and two angles. So you're going to either put A with B, A with C, or B with C. You would have to know 3 of the 4. So you'd have to know the two sides and the angle, or you would have to know the two angles and a side in order for this to work. So, all right, let's look at the example we have in example 1 here. Let's see what we're given. So, all right, let me just sketch the triangle ABC. So it gives me that angle B is 34 degrees, angle C is 82 degrees, and side A is 5.6. So I'm just going to draw a triangle here. So I'm going to call this angle B, which is 34 degrees. Angle C, which is 82 degrees. And this would be A, and we don't know right now. A is 5.6 inches. And that's it. That's what I know. All right, so again, this is a case of angle, side, angle. So that's how I know. I know I can use law signs. All right. So since I don't know, they don't give me A, but I know A because I can just do the 180, and we know there's 180 degrees in the triangle. So if we add 82 and 34 together, that's 116. 116 from 180 is 64. So this angle is 64 degrees. All right, so I know angle A and the side across from it, which is side A. I know angle B, which would allow me to then find side B. If I want to solve it, this one just says find the length of side B, so I don't have to solve the whole triangle. So I don't need to find side C. I could, but I don't have to. I just want to find side B. So I'm going to set up A over the sine of A equals B, side B, over the sine of angle B. All right, so let's fill in what we know. So we know side A. We know angle A. So the sine of 64 degrees. We know don't know side B. That's our unknown. That's what we're trying to find. But we know angle B. So sine of 34. So in this problem, I knew the two angles and the one side, and I could find the other side. All right, so anytime you have a proportion, you know the cross products must be equal. So that times that must equal that times that. So B times sine of 64 degrees equals 5.6 times the sine of 34 degrees. All right, so and then all I have to do is divide by the sine of 64 degrees, and I will know angle B. Side B, I'm sorry. All right, so sine of 64 degrees. So I go to my calculator now and type this in, and that's going to be B. So let me click over to my Desmos calculator I have on here. I need to switch it over to degree mode because my angles are in degrees. And all right, so I have 5.6 sine of 34 divided by sine of 64. I can get that. I'm going to divide that by 6 sine 34 divided by the sine of 64. And so 3.4, I'll say 3.5. I don't know where it said around 2, but it didn't say. So 3.5 would be my length of side B. And that is on that one all I had to find. All right, example 2 says find the missing parts of triangle ABC. So we got to find all the missing parts this time. All right, so in this one, I'm given 2 angles. So let me draw this out here. So this is A, that's 46 degrees. This will be B. Actually, let me make this B. And this C, 78 degrees. All right, and I'm given side B always across from angle B. So this is 7.5. And I can again find because if I got this side, I would want to know the angle across from it. So 78 and 46 is 124. And 180 minus 124 is 56. So this angle is 56 degrees. So angle B, 56. That's one of the parts I got to find. All right, so I also have to find, let's see, side A and side C, because I know side B. And that's all I've given. So I've been given 3. I was given 3 parts. I'll find the other 3 parts. Okay, so let's find. So I know side B and I know angle B. So I'll start with B over the sine of B. So 7.5 over the sine of 56 degrees. Maybe I should write this out. B over sine of angle B equals. So it depends if I want to find A or C first. Doesn't matter. I'll do A first. All right, so equals A, which is what I'm trying to find, over the sine of angle A, which I know is 46 degrees. And then I'll work that out in a minute. And the other one I'm going to do 7.5 is to the sine of 56 as C is to the sine of 78. All I got to do is cross multiply and solve then. So A times 56 times the sine of 56 degrees is equal to 7.5 sine of 46 degrees. And then all I have to do is divide both sides by the sine of 56. All right, so I would go to my calculator, type that in. I'll have that answer, and then over here I'll have C times the sine of 56 degrees equals 7.5 sine of 78 degrees. And then I divide by sine of 56 degrees. And I'll have C equal to, so I just need to type that in my calculator. So 7.5 sine of 46 sine of 46, 46 I mean, divided by the sine of 56. Let me double check and make sure it's right. 7.5 sine of 46 divided by sine of 56, yes. And that is 6.5. So let me jot that down, 6.5 for side A. All right, now side C is 7.5 sine of 78. So the 7.5 is going to be the same. I just got to change the angles to 78 and 56. 78, no, that stays the same. 8.8. 8.8 here. And this one is 6.5. All right, so given angle A, angle C, I was able to find angle B, the third angle, and given side B, I was able to find side A and side C. All right, example 3. This one's got a little diagram here for us. So the law of sines, along with some fancy electronic equipment, was used to obtain the results of some of the field events in one of the past Olympic Games. For instance, in the figure below is a diagram of a shot put ring. The shot is tossed or put from the left and lands at A. So here's the circle where they throw from. Shot put goes up, lands at A. A small electronic device is placed at A. There is usually a dent in the ground where the shot lands, so it's easy to find where to place the device. The device at A sends a signal to a booth in the stands that gives the measures of angles A and B. So here is angle B up here. So somebody's up here in the stands, and they can measure the angle formed between those, and then the distance is found ahead of time. With this information, we have the case angle side. To find the distance, use the law of sines to find the distance. X if A, so A, remember, is this distance right here. So they've already measured that prior to. They know how far it is from the booth to the shot put ring, to the edge where it's measured from. And we know angle B, and we know angle A. And so we want to find the distance that the shot put traveled. So basically we want to find side B on the triangle. So it's really, and all that big long explanation is literally just a law of sines problem where you know angle B and angle A, and you know side A, and you're trying to find side B. So let's draw it out here just where I can see it a little better. So let's zoom back out. All right. So in the triangle, let me just draw it a little better over here. It's not a good triangle, but it'll work. All right, so this is angle B up here. This is angle A. So we'll call this C. This is where they're throwing it from. That's the shot put ring. This is where it lands. So this is side B, and this is side A. And so we know that side A is 738 feet. They measured that prior to, just from the booth down to the edge of the shot put ring, where they throw from. We know that angle B in here is 6.3 degrees. And we know that A down here is 78.4 degrees. So we want to know how far they threw shot put. So let's see, we've got side A and angle A. So we're going to say A over the sine of A. And we've got angle B. We want to find side B, so we want to do little b over the sine of big B. So we know little a, and big B, and we're going to find little b. So it's very straightforward law of sines. So A is 738. Angle A is 78.4 degrees. Side B is what we're trying to find, and angle B is 6.3 degrees. All right, so we cross multiply. So we have B sine 78.4 degrees equals 738 sine of 63 degrees. And then we divide by the sine of 78.4 degrees. All right, so I just go to my calculator now, and I'll type in 738 sine of 63 over sine of 78.4. 738 sine of 63 divided by sine of 78.4. 671. Doesn't say where to round to. Well, if we keep significant digits, we'll go one decimal place. So 671.3. Will be the, and that is in feet. Okay, I realized that when I typed this in, I typed in, it's the sine of 6.3. I was going to say, that's a long way to throw a shot put. I don't think so. I typed it in as 63 instead of 6.3. So scratch the calculation there. This is, let me go back to my Desmos. I fixed it right here. So I had 63 degrees. It says 6.3 degrees. So it's 82.7. That sounds a little more realistic. 82.7. All right. Okay, example 4. So this one, looking at the diagram here, we have Earth and a satellite out here off of the surface of Earth. So a satellite is circling above the Earth as shown in the figure below. Here's the satellite at A. When the satellite is directly above point B, angle A is 79.2 degrees. So we're given this angle right here. Let me go ahead and draw the triangle out here. I want one just so I can write on out here. And we'll label this. So this is C, that's center of Earth. This is D, this is A. All right. So we know angle A is 79.2 degrees. If the distance between points B and D on the circumference of the Earth is 1,050 miles. So what they're talking about is this distance right there from B to D is 1,050 miles. And the radius of the Earth is 3,960 miles. So from center to Earth, this is 3,960 miles. How far above the Earth is the satellite? So we are looking for this distance right here. So really, this is not a side of the triangle, but this is the side of the triangle. So if we find this whole side, D, all we would have to do would be subtract the radius, and we would know what that distance from the surface of Earth to the satellite is. So I basically need to find side D. All right, so the problem is I have this angle and this side. So I have side A and angle A. I need to find side D. That means I need angle D. I need something else, in other words. I need another angle. It doesn't give it to me, but it gives me this piece of information that it gives me the length of this arc from D to B on the circumference of the Earth is 1,050 miles. So what is that going to do for me? So that basically gives me this angle in radians. So remember, a radian is the radius. So 3,960 miles is a radian. So this is not quite, this is almost a fourth of a radian. So it's 1,050 miles out of 3,009. It's 1,050, 3,960 of a radian. So that's how many radians this angle right here is. Now, we need it in degrees. So remember how, if you're in radians, how you change it to degrees, you multiply by 180 degrees over pi radians. So this is how many radians. So it's not, or it takes 3,960 miles to make a radian, and this is only 1,050 miles. So it's going to be a fraction of a radian. And then once I've got it in radians, I can multiply by 180 degrees over pi radians, and that would then change it into degrees, which is what I need. So I need to do the math on this right here. All right, so let me type that in my Desmos here. All right, so I need 1,050 divided by 3,960 times 180 over pi. All right, 15.2 we'll say. All right, so this is 15.2 degrees. And that is this angle here, 15.2 degrees. All right, so I really need angle D since I'm trying to find side D. So, but I've got it because I know angle A is 79.2 and angle C is 15.2, and that is 94.4. And then 180 minus 94.4 is Let's see. 85.6 degrees. All right, now I have enough information to set up so I can say A over the sine of angle A equals D over the sine of angle D. So little a is 3,960 feet over the sine of angle A, which is 79.2 degrees, is equal to little d over the sine of angle D, which is 85.6 degrees. So when I cross multiply, I'm running out of room. So let me come over here. So I'm going to have d times the sine of 79.2 degrees is equal to 3,960 times the sine of 85.6 degrees. And then if I divide both sides by the sine of 79.2, we're ready to calculate. All right, so 3,960 sine of 85.6 divided by sine of 79.2. Oops. And that is 4,019.5. 4,019.5 miles. All right, so I didn't finish this problem. Remember, we're looking for the distance from the satellite is from the surface of Earth. So this is the radius, 3,960. This is x. So I really need to take 4,019.5 minus 3,960 to get the actual answer. And let me just calculate that real quick here. So 4,019.5 minus 3,960 is 59.5 miles. Is how far the satellite is from the surface of Earth. 4,019.5 is the distance from the satellite to the center of Earth. All right, example 5 is really get a little physics comes into this, some vectors. And so the math part of it, the law of sines, using the use of law of sines is pretty easy, no different. We've done all the other ones. Getting this one drawn right is the critical part. So it says a traffic light weighing 22 pounds is suspended by 2 wires as shown in the figure below. The magnitude of the tension in wire AB, this is wire AB, call it T2, and the magnitude of tension in wire AC, so T1. All right, so we assume that the light is at static equilibrium. And so because it's at static equilibrium, it's not moving, then the sum of the forces acting on it has to equal 0. So because of that, we can redraw this as a closed triangle with the 2 vectors being sides of the triangle and the gravity force of the light being the third side of the triangle. There is a good little animation of this in the ebook I was going to show here. If you hit play here, you can see that here's your 2 forces, the tension of each one of these wires, and then the weight, the gravity of the light, the force of gravity. And so if I hit play on this, you will see how this transforms into how we could draw this as a closed triangle with the tensions and the force of gravity being the three sides of the triangle. We can make it into a closed triangle like that. So your force, this is going to be your 22 pounds or whatever the force of gravity on the light is. And then the other two sides of your triangle being your tensions. All right, so let me go back and let's draw this one out like that. All right, so we have, so as we shift this line over, that's going to be our 22 pounds gravity. All right, so this vector, which was this one, is going to be our T2. And this is 45 degrees. And so this is 45 degrees. And then this vector, which is acting this way, and this is 60 degrees. So this would be 60 degrees. And this is T1. So this is how you would draw it as a closed triangle with the three sides being the force of gravity, the light, and the two ropes providing the tension. And so we are asked to find T1 and T2 basically. So it comes down to just being a law of sines problem because we can find third angle here. 45 and 60 is 105. 105 from 180 is 75. So we know this angle here is 75 degrees. We know the side opposite. So we've got side. So let me call this A, B, C. And so this would be B, and then obviously this T1, T2. Okay, so we've got B over the sine of angle B equals, so T1 would be little a over the sine of angle A. All right, so B is 22 pounds. Sine of angle B is 75 degrees. Little a is T1, and sine of angle A is 45 degrees. All right, and that will allow me to find T1. And then for T2, I could do the same thing. B over the sine of B equals C over sine C. So B is 22 over the sine of 75 degrees is equal to little c over the sine of angle C, which is 60 degrees. All right, then just cross multiply and solve it. So this is going to be, this one's going to end up being T1. I'm going to go ahead and just, you're going to cross multiply this way. So 22 times the sine of 45 degrees divided by the sine of 75. And this is going to be 22 sine of 60 divided by sine of 75. All right, so I'll calculate that. I'll calculate that. All right, so 22 sine of 45 over sine of 75. All right, 16.1. That's T1 pounds, and T2 22 sine of 60 over 19.7. Okay, so 19.7 pounds of force and 16.1 pounds of force, depending on where they want you to round. Now, if they wanted you to keep significant digits, it'd be 20 and 16. Okay, this is example 6. I actually have it labeled as 5, to number 5, so this should be 6. This is our final example. All right, this one, the diagram, I'll warn you right now, is a little complex, and that is simply because they have one triangle that's supposed to be flat on the ground and the other is three-dimensional, so it's kind of coming up out of the. So what's going on in this one is you have this hot air balloon that's flying around. It's 450 feet above the ground. So this is your hot air balloon right here, and it is 450 feet above the ground. It goes on to tell you later in the problem that the angle of elevation to the balloon is 12 degrees. So it's kind of like you have this, if you could separate these two triangles, because it makes the diagram really complicated when you got it on top of each other. So the angle of elevation from point A to the balloon is 12 degrees, and the balloon is 450 feet above the ground. All right, the other triangle here is on the ground. So if you read the problem, what it's saying is that you run out of gas at point A. And notice the north-south line, the east-west line, they're not straight up and down. And this is because they're trying to make it 3D, because I've got this triangle here that's perpendicular to the ground because it's the altitude of the balloon. And you got this one that's on the ground. So they have to draw it that way in order to make that work. So if you're at A and you are run out of gas and the nearest gas station's at B, and so the balloon, this is directly under the balloon here at C. So it goes on to tell you that the angle from the balloon, the bearings of the balloon from point A, where you ran out of gas, is 13 degrees east of north. So remember, this is north, this is east. So 13 degrees east of north is that. And the point where the service station is, the bearings of the balloon is 19 degrees. This is south, so this is east of south. So those two angles are given, and what we want to know is how far is where the car ran out of gas, is it from the service station? So this distance AB is what we want to find. So this whole triangle is on the ground. Well, right now we have two triangles, and then I, of course, this, if I pull that triangle out, this is A, B, C. And I know this is 13 degrees, and I know this is 19 degrees, and this would be 13 and 19 is 32, so this would have to be 148 degrees. And this is what I'm trying to find right here. I'll call it X. So I'm trying to find AB, the distance from the car to the service station. This is just on the ground. So if you just take the two triangles apart, this one is elevation. It's perpendicular. This is the ground. It's perpendicular to the ground, and this one is completely on the ground. So that's what makes this whole diagram look so confusing. So the problem is I don't have enough information to find X yet. Now I know the angle across from it, so I know I need X over the sine of 148 equals, I need some side. I either need AC or BC. I can't do this with two sides being unknown. So when I look at this is C right here, by the way. This was A, this is D, where the balloon is, and this is directly under the balloon. So what I see is that I can use this triangle to find AC. And if I know AC, then I know AC over here, and that gives me the other side. So this will be whatever AC is. I'll fill it in a second, over the sine of the angle across from AC, which is 19. So I need to find AC using this triangle before I can finish this off. So this is a right triangle, so I don't need any law of cosines or sines or anything like that on this. I just need a basic trig. So this is, the angle is 12, the opposite side is 450, and I need to know the adjacent side. So opposite and adjacent, that's tangent. So I know the tangent of 12 degrees is equal to opposite over adjacent x. So when I multiply by x, and then I divide by tangent 12, so I would need to know what is 450 divided by the tangent of 12. Calculator. All right. 2,117. 2117. Okay, so I'm going to fill that in. That's AC. 2117. So I'm going to fill that in over here. And now I can fill in AC because now I know what it is. And then I can cross multiply and solve this. So X times the sine of 19 degrees is equal to 2117 times the sine of 148. And then we'll just divide by the sine of 19. All right, so I've plugged that into my calculator, 2117, 148. By the sine of 19, I believe it was. Yep, 19. All right. So I get 3445.8. All right, and this one doesn't specify where to round to, so I'm just going to leave it as it is.